Okay, and do we have video?
Can you hear me as well?
We can hear you. We cannot yet see.
Perfect. I think that it would be better to have my slides in full screen so that you can read the code
That
easier.
makes sense. We will switch to that view. Perfect. Okay. Our next speaker will be Arnaud, who's going to tell us about a program logic for OCaML so we can verify OCaML programs.
Hi, so thank you for having me talk today. And today I will present a tool called Osiris to verify OCaML programs within the Coq Proof Assistant. And this tool has been written by François Pottier, Armaël, Guéneau, and myself. And while some tools some verification tools are based on automatic solvers, such as Y3, for example, in the ML community, other projects and our tool will allow users to write manual proofs about their program using deductive reasonings. And everything takes place in the Coq Proof Assistant. So just as a reminder, in a proof assistant, people can put statements they would like to prove here about their programs, and then they can script a proof using so-called Coq tactics. And afterward, the proof assistant will make sure that the proof is indeed correct. And in our tool, we use a Coq framework called Iris because it contains a lot of built-in proof techniques to help with program verification and automatically handles divergent programs, program manipulating a heap, and so on. And we provide these features, we forward these Iris features to Osiris users. Before going any further, I will explain what we mean by to prove a program and to verify a program. For us, to verify a program is to explain the behavior of the program. Usually, this is done by writing specifications on program and then proving them. And these specifications are horse-star style specifications, so they contain a precondition, that is a condition under which the program has been proven correct and safe, and a post-condition which provides information on the result of some computation. For example, for a length function computing the length of a list L, you can call the length function on an OCaML value v, which represents some list L, and the result will be the length of the list. And when we verify a program, we should make sure that the proof ensures the safety of the program, so there should be no runtime crash, its progress, that the program will never get stuck, and that the program will satisfy its post condition. And there already exists some previous work to allow such proofs within the Coq Proof Assistant. CFML2, for example, allows for interactive proofs of OCaML programs, but it does make some choices about the semantics of OCaML, which we do not in Osiris. And it doesn't have access to the Iris logic, which we want to prove because it is highly expressive and helps verifying difficult and complicated programs. Also, Iris, the framework Iris has already been used to help verifying small ML-like languages, programs written in small ML-like languages, and to verify and reason about very specific aspects of the OCaML language, which are difficult to handle logically. Our contributions with our tool, Osiris, is to provide a proof methodology to prove real-life OCaML files and within the Coq Proof Assistant. And in order to do that, we had to define an original semantics for the language and to provide a program logic which has been defined from the Iris logic. In this talk, I will provide this proof methodology I just talked about and show how to verify a small OCaML program, a small example. And then I will focus on the structure of the project and how it was actually written, that is to define our semantics and provide the program logic we use. But keep in mind that the project is still very young and it is still a prototype at the moment, so we do not have support for the whole language, nor could we use the tool to verify projects right now and large modules. The proof methodology is quite simple. Indeed, we just want to work on some OCaML files within the Coq Proof Assistant. So the first obvious step will be to fetch the content of the OCaML files and to get them in the Proof Assistant to be able to work with them. This is done by a translation tool written in OCaML. Then users of Osiris might write specifications about the files, which we see as modules, and the functions defined within the files. Such a specification could look like the specification of the length function we have seen earlier, for example. And then users will use our Coq tactics to prove these specifications. When it comes to the translation process, The process is very easy and straightforward so that people can actually read the translation of an OCaML file. It just retrieves the type tree of the OCaML file to translate. Then it will convert the AST into an AST of our own, which has been defined within the proof assistant. And finally, it will dump the result into a COG file. And then users who want to actually prove things about these files can refer to this definition afterwards. Then they can write specifications. I will not dwell on how to specify such modules right now. Instead, actually, I won't do it at all. Instead, I will focus on an example of a toy module, simply containing a length function computing the length of a list, a small list declaration, 1, 2, 3, 4, and then we just compute the length of the list. In order to specify such a module, users can just simply say that this module should at least contain a function called length, and that this function should satisfy the correct specification. And what we call to verify this module using our tool is to provide to execute symbolically the module. So we interpret the OCaML program within the proof assistant, and the evaluation will stop at some breakpoints so that users can actually provide proof statements or perform some logical work. This evaluation, some of the breakpoints occur, for example, at function calls, so that users can use for specifications which they might have proven before, or at late bindings, so that users can actually prove things about their programs. And finally, sometimes the evaluation will simply stop because it needs a little bit of help from users. For example, when the heap is modified, or when some non-deterministic construct of the language is used. In this example, you don't need to read all the comments of the proof script, but here is how a proof would go in Osiris. You would first launch the evaluation using the WP tactic. Then you would say to the tool that you want to specify the length function using ospecify for Osiris specify. I've omitted the proof, which is by induction over the list. And then the evaluation will keep going with this function, and the Osiris knows how it behaves. It forgets its actual body, and the evaluation will just start again. Then it will stop when Lily gets evaluated, so that we could potentially eventually prove some specifications about this list. We don't want to, so we just use WP continue to ask it to continue the evaluation. And then we have a function called toLength, and we can use the aforementioned specification with WP use. Then the evaluation continues, and we are done. Afterwards, we get an OCaML value representing the module, and we need to prove that this value satisfies the pass condition we set, which is trivial here because obviously the module contains a length function, and we have already proven its specification. Now that we've seen the tool work on a very small example, I will briefly discuss how we actually wrote the tool and what were the steps that we had to follow. So the goal, please keep in mind that the goal was to prove OCaML programs using COG tactics within the proof assistant. So the first thing we need to do is actually to explain what we mean by to prove some OCaML program. I spoke of behavior earlier, but right now we just have syntax. So we need to give meanings to the syntax by defining the operation semantics of the language. Then we define reasoning rules to reason about the semantics and the programs. And these rules are proven to be correct with regard to our semantics. And afterwards, we will define COG tactics to exploit the rules so that the proof we obtain will be correct by construction because it only relies on correct rules. So let me describe the semantics briefly. Most Iris instances use what we call a small step semantics, which describes the step-by-step evaluation of a program. For example, the expression 1 plus 2 has to reduce to the value 3. But this is quite tedious for large language, especially with OCaML, because there are a lot of transitions to consider because of the size of the language, and also some transitions which are very difficult to write. For example, with pattern matching. How do we explain how pattern matching the match steps into the program is difficult. An orthogonal difficulty is the presence of non-determinism within the OCaML semantics. For example, when you call a function E1 applied to E2, we don't know whether E1 has to be evaluated before or after E2 is. So our solution to tackle these two issues is to write a semantics in 2 steps, each tackling one of these issues. We call this semantics an ample step semantics, which automates some of the steps we would see in a small step semantics. The first step of the ample step semantics is to evaluate OCaML expressions in a smaller language, which we call micro A, and which is much simpler than the OCaML expressions and syntax. This allows us to use the proof assistant to compute some of the steps for us. For example, arithmetic operations are computed automatically. This is done by the eval function, which takes an environment describing the variables at hand, an OCaML expression, and returns the computation represented by the expression. This computation will return an OCaML value, which is why it is of type microval on the slide. This first step is also used to evaluate pattern matching, so that we won't have to reason about it later on, and to evaluate function calls as well. And then the second step of the ample step semantics is to describe the behavior of these very simple computations using the step relation, which one can see here. It will explain how a computation of type macro A and the OCaML heap can evolve step by step. To better understand what a computation here for us, a computation is either a value using the return construct, an error using crash or next, a parallel computation, M1 and M2 computed in parallel. If they succeed, the continuation K is called. And finally, a possibility to perform system calls which implement OCaML features which cannot be implemented by the first step of our semantics. These include heap manipulations, potential divergence, and some non-deterministic binary choice of the semantics. Please keep in mind that we only verify sequential programs. So the PAR construct here, even if it represents programs, computations performed in parallel in our semantics, doesn't mean that it is parallel, that it represents parallelism in the source file. To better understand this, let's use an example of the function call I discussed earlier. If you apply the expression E1 to the expression E2 in OCaML, E1 could be evaluated before or after E2. And our solution to handle this is to consider that it doesn't matter and we'll just evaluate them in parallel. And should these computations return values V1 and V2, then we will perform the function call V1 applied to V2. And this is how we describe the OCaML language in two steps, so that we have very few transitions to consider, and we ask the proof assistant, the Coq proof assistant, to compute most of the steps, and only stop and ask for explicit steps within the computations whenever something interesting happens within the language. And to prove an expression, we first evaluate remember the toy module, we evaluated the module and stopped at some points, where here is the same. We evaluate the expression E into a computation of an OCaML value, and then we prove that this computation is safe, and that after this computation, some post condition will hold. And this after keywords, this after predicate, will ensure everything we wanted to prove about our modules and expressions. In order to reason about OCaML programs and computations, we do not need to know exactly how after is defined. Instead, we use a set of reasoning rules which might be used in proof scripts afterwards. For example, if you want to reason about a single value, then the computation is done, and you simply need to prove that the value satisfies its post-condition file. This is the right rule one can see. If you have some reference, if you want to write some reference within the source file, then this will be translated as a system called calloc, which we can see in the alloc rule. And calloc vk represents an allocation of a reference which should point to the value v, and the rest of the program is contained within the continuation k. And in order to prove that this is safe, we need to prove that for any location L, if L points to the value v, then the rest of the program is safe and satisfies the post condition that we have. But I also put another rule here, the PAR rule, to discuss parallelism and parallel computations. Again, this is to represent non-deterministic choices in source programs in the semantics of the source file. But this rule is difficult. I won't even read it, and we can just see that it is a pain to apply such a rule. And but what we also know is that at every functional call, we will have a PAR construct that will appear, and it also appears at every tuple declaration. So what we want to do is to simplify programs so that we never see non-deterministic choices of the semantics when we verify a program. In order to do that, we have defined an alternative program logic for pure deterministic programs. Simp M1, M2 means that the computation M1 performed by some OCaML program can be simplified into the computation M2 deterministically and without modifying the OCaML heap. And this is also usable to prove the after predicate. So if M1 can be simplified into M2, then it suffices to prove M2 to prove M1. The main use for the simp predicate is to simplify programs, as we can see on the bottom of the screen. If you consider the expression 1 plus 2 plus 3 plus 4 plus 5, there are 8 function calls in total in OCaML, which means that there will be 9 branches to consider in a tree of power constructs. And this is not possible to work with it and to apply the rule we've seen earlier. So we use simp automatically in the proof assistant, and there are a lot of lemmas to help us out to simplify this directly into the value 15. Simp can also be used for program specification, but I will not dwell on this possibility. Instead, I will provide some short and long term, the state of the project, and provide some short and long term goals for the project. So currently, the project supports a part of OCaML, a fragment of OCaML, containing several features, but not all of them. So we would like to add support for more OCaML constructs and features. And the very, very long-term goal would be someday to incorporate previous work to reason on these very difficult OCaML features, such as effects or garbage collection and so on, which have already been tackled by other projects using Iris. But this is not possible currently in our project. So we'd like to do this, but this is a very long-term goal. We are definitely not close to performing such tasks. And in conclusion, although we support a few OCaML features you can see on the screen, we still need to test, to write a lot of tests and examples about these constructs to make sure that we are able to reason it in an ergonomic way for users. And the immediate future work will also be to better understand how to verify, use, and specify modules in a way that is, again, ergonomic for end users and useful for us in order to automate some parts of the proof. And this will be all, and I think that I still have a few minutes left. Should you have any questions?
Thanks very much for the interesting talk. Do we have questions? Okay, I have a question to get us started. So you've indicated that the in some cases the evaluation order of OCaML programs is unspecified, like the evaluation order of function arguments. Of course, in practice, OCaML has the very natural right to left evaluation order, as everybody's familiar with. And in my experience, some programs depend on this. Is there any way to sort of modify the semantics so that we could
it would. The key idea was to be as close as possible to the description of the language, and to make sure that programs do not rely on this evaluation or on these choices which are made by the compiler to be correct. And even in assertions, for example, you could run you could have some expressions within assert keywords which produce some effects like modify references and so on, and rely on them to be correct. But these could be erased at compile time if you pass some option to the compiler. So we don't want the programs the correctness of a program to depend on these choices.
Understood.
I don't know if that answered your question.
Yes, it did. Thank you. Pierre has a question.
Hi, thanks for the talk. Do you have a semantic for the unsafe part of OCaML?
Not yet, no. All of the features we use and support are at the top of the screen right now. But the semantics still needs to be enlarged for new constructs of the language.
Hi, thanks for the talk. Do you plan to also support the semantics for infinite values, like defining an infinite list?
With the letrec for values.
Yes.
Yes. Well, we currently support recursive functions using letrec, but not infinite values. But it is something that we've already discussed. And the idea would still be, of course, to assert that we can handle the constructs we already have in our semantics before extending it. But it is something we would like to do at some point, yes, to have recursive values.
I have another question. I don't see in your list of currently supported or future work parallelism. Is there simply no hope, or might we get there?
There is hope. We just don't support it yet because we still have to mimic function calls to get functors, which we do not have, and other features we want first, like exceptions. But then at some point we would like to allow this in our semantics as well. But it is not currently supported. Yes, it is on our to-do list.
Okay. Looks like there are no more questions, so let's thank the speaker again.